Hey everybody, welcome to the very first video within the system design series, and within this series we'll be taking up some real world applications and we'll be using them as our preparation material for system design interviews. So within this video we'll be talking about payment systems and how we can design payment systems. So whenever you're handed a system design problem, it's always wise to break it down into certain key components upon which you can build up your whole case or whole conversation before you jump into the interview. So let's sort of list them down, and I'll start from scalability, which happens to be the very first one. Second one would be availability, although they both go hand in hand, but it's better to sort of list them out and then sort of build the whole case, as we'll discuss just in a bit. And the third one would be reliability. The fourth one would be fault tolerance. And finally, the fifth one would be data integrity slash encryption. So whenever I'm handed a system design problem, these are the 5 key components that I like to focus on. It sort of gives you a trail of thought, a train that you can chase, and it's easier to sort of start from scalability and then eventually end things up to data integrity or encryption. Okay, so let's lay out what we mean when we say that we're building a payment system. So let's say you have a e-commerce application. This is your e-commerce app, which sort of communicates with your payment system. And so what happens here is that you get all the functionality here. You have your products here, you have your cart here, and this is your checkout function. And as you check out, you are in the zone where you're dealing with your payment system, and you have to make sure that you know how things go from here. So what happens next is that your payment system has another set of direction, which sort of it can take its course over there. That course would be a particular payment system provider, normally known as PSPs. These can comprise of, some of the popular ones are Stripe. And so normally, so what it means is like a PSP is just a provider that provides you the compliant based and regulated solution upon which you can base your payment system. So mostly everything goes here. This can involve risk checks, fraudulent activity detection. So basically, this is what they take up. It's all their responsibility. If you're building a payment gateway from scratch, you might end up into a lot of different problems where you actually enhance the scope of your problem, which means that you have to take care of compliance, you have to take care of all the integration and some third-party integration, which can include knowing your customer, which is known as KYC. I should add it over here as well. But if you're using a PSP or a payment system provider, it's already taken care of. So all you need to do is sort of just worry about how to integrate it within your application. But that is not the end of the story, because you have to deal with your payment events, and you might need to track your payments and sort of store them in a viable format, and take care of some stuff around data integrity and a lot of factors that we have listed over here. So normally now the very first question would be that, hey, if everything is being taken care over here, then why do we really need to worry about this? Well, let's say that being in an e-commerce application, you always have to raise an event which actually lands up to your payment system. Now, everything is based on this particular event. And the successful event would be the one that lands over here. So designing a payment system is all about this particular event and the story around this event and the journey of this particular event. We have to make sure that this particular event makes it to the PSP, and it goes through all these different aspects. So designing a whole payment system is basically just about this, that how you actually make sure that your event is not lost, that your event is properly stored within your database, that your event does not fail to actually reach the PSP. If it fails, then what are the steps that we can take to sort of ensure that this event actually lands up to its destination? So this is what a payment system is basically all about. And this is what we're going to focus within our system design problem, basically. So I hope this bit is clear. Let's take this further and let's talk about the next steps. So we'll start with scalability. So now, since we're talking about scalability, we know that this particular application or the payment service in general exists as an independent service, or it would sort of exist as an independent service within the whole architecture. So how do we go about it? So we know that this payment service, if it's an independent service, if it exists as an independent service, it would face the challenges or bottlenecks of network, latency, storage, and computing itself. So whenever we have high traffic or high low traffic, we're dealing with networks. Whenever we want something to be, our website or our service to be accessed in less amount of time, we're talking about latency, storage. We're dealing with what are the integrations that we're gonna talk about or we're gonna focus on in terms of storing our data, which would be NoSQL or our relational databases if we don't opt out for the NoSQL model. Computing in itself is our particular compute engine or our compute instance enough for the incoming traffic. So this sort of, both of them are sort of interlinked. So as an independent service, the very first thing that we're going to talk about is that, okay, if we have a application, just like we discussed above, and if we have a high traffic, then we want to go for a horizontal scaling. and this can exist within an auto scaling group, or if you want to manage it yourself, which I don't know if you should, but just for the sake of theory, you can go for multiple instances of your payment service, which can either increase or decrease upon demand. So this is your payment service. Let me add a quick label here. And this is your e-commerce application. Cool. So we have our horizontal scaling group over here. Payment service. Forgot to add that. Sorry about that. All right. So since now we have multiple instances of our payment service, we have to think about something in terms of, balancing our incoming traffic. So this would basically translate into something like, let me get rid of this. And let's add a load balancer over here, which would take care of your instances at a front face. So this can be an L4 load balancer, since we are already within our application and we just want to communicate with our compute instances. So the network layer load balancer would suffice. And eventually, since we're talking about network, and we're talking about network, and we are talking about computing within our current problem at hand. So obviously, having one database would always be a problem if we are sort of reading and writing to one instance. So with high traffic, obviously this would be a problem, because your read and write operations can vary. If your read operations are high and your write operations is low, then obviously your database instance itself would be busy most of the time, and it would spend a lot of computing power just to sort of figure out a balance between both of them, which is not the wise thing to do. So what we can do over here is that we can sort of add a master database where all the writes can go. So if I have to write, I can write over here. And along with the master database, we can have a read replica, depending on our needs. Different, cloud providers sort of provide a replica group as well, which can sort of expand and, shrink as per your need. For example, AWS enables you to have like 15 read replicas. And so we can plan something out depending on your cloud provider or your whole tech stack in general. But I think it's something that's not a big deal, since all of these replicas can exist like in one availability zone, or they can vary. If you want to make your application foolproof, and if you want to sort of protect it from any sort of disaster occurring, or in terms of disaster recovery, if you want to plan stuff out, then you can have this in one AZ, and you can have it in different AZ or region, depending on your need, obviously. But yes, this sort of comes into the section of fault tolerance, but if you want to pane this out this way, then it's totally fine. So all your read reads can be distributed, across these replicas. So this would be, this sort of addresses our network and computing problems. So what else do we have? This also address your storage problems. For latency, obviously, whenever we're creating these replicas, as I suggested, that you can sort of plan these to be, in different availability zones or regions. And so you can always choose the availability zones or that are closer to your proximity, which sort of would help the latency factor as well. In terms of scalability, I believe, given the scope, these are some general do's that we can sort of follow. We have addressed scalability over here, and along with scalability, as I depicted in the very start of the video, availability goes hand in hand with scalability. So what we have done over here is we have made sure that if you're putting our read replicas or our instances in different availability zones or regions, then we have sort of addressed the problem of availability as well. So if even when we talk about having everything in one availability zone, and if something like a disaster happens, then there's a high risk that, all these resources can just, die. And you won't have access to your databases, you won't have access to your compute instances, which sort of is not the best practice whenever you're designing a problem to be available. So just to make sure that you don't miss this out. Also, we have touched a bit on fault tolerance as well. Not entirely, but we'll discuss some other factors over here as well. Cool. All right. So what do we have next? Next, we have reliability. All right. Reliability. Let's scroll down and let's talk about reliability. Okay, so what we actually mean by reliability over here. For example, let me select a different color. So this is your application, and it's communicating with your payment service, and it's sending out a packet, a data packet over here, and some of these packets get lost when you are sort of communicating with your PSP. So what happens next? That's the question, or these are the solutions that we're going to explore within the whole reliability section. So do we retry? If we retry, then what is the protocol over here? How many times are we supposed to retry? Or what are the methods that we need to ensure while we're retrying in delivering a particular data to our PSP? And along with that, if your data is corrupted, then what are we supposed to do over here? Or what happens if this particular data fails and user is not, informed about it? Then what does the user do? It would try to send this data again. And if sort of this data has reached the PSP over here, but it has failed to sort of, make it to another third-party service, for example, KYC or, some fraud detection services that might be, a part of PSP, then how can these systems sort of ensure that, although this is not our concern, whatever happens over here within the PSP, but in generality, it's good to know that what are the measures that PSP already takes, and what are the measures that we can take to make sure that, we can ensure the on-time delivery, and we can ensure a sure shot delivery. So let's talk about that a bit. All right. So if the data fails to sort of, land in your PSP zone, that what are the measures that we need to take? Obviously, we need to retry. Yet we don't have to inform the user, but we have to maintain a protocol where we sort of retry to deliver our data to PSP. Now, some of you might be saying that, okay, we just immediately try to bombard PSP with our data again, and we just keep our pace from there. We just throw in the data again. Hey PSP, this is my data. Hey PSP, hey again, this is my data. Hey PSP, this is my data. What we need to understand that accidents can happen, and PSP itself is a service. It exists as a service, and some components might have failed at their end as well, which might not be fixed immediately. So we have to make sure that we are using certain type of a protocol. So whenever you retry, there are two particular approaches, the two most important approaches that you can follow whenever you're trying to, deliver your data again. So the very, very first approach is the incremental approach. And the second approach is exponential backup. Normally, exponential backup is the most used whenever you're trying to deliver your data again. Exponential backoff. So exponential backoff looks something like this. So just like an exponent graph, I hope I've done it right. Yeah, that's the exponent graph. So it goes up to 2 power of n. So which means that if it's 1, you have to do it in 2 seconds. If n is equal to 2, you have to do it in 4 seconds, and it increases just like that by the factor of 2. So it sort of gives you a breathing space. That it gives both components, the failing component, which happens to be on the PSP's end, and the other component being the payment service itself. So it sort of gives both of these services a breathing space where they can sort of, it's like, hey, PSP, here's my data. No response. All right, I'll just wait. And you wait for 2 seconds and, hey, PSP, here's my data again. No response. All right, I'll just sit back. I'll just relax a bit. 1, 2, 3, 4. Hey again, PSP, here's my data. And guess what? PSP is back. Yep, I'm accepting a request. What's your request? I'll process the request, and boom, here you go. Incremental is something that comes before exponential backoff, because it sort of goes something like this. So if you're on 1 second, if nothing happens, then the next you wait for 2 seconds, and if nothing still happens, then you wait for 3 seconds. So it's sort of incremental. But I think the exponential backoff it makes more sense in terms of, the wait time. Meanwhile, you can just show the users the thing that they love the most, which happens to be the loader. So no, users don't love it. Just a joke. All right. So yeah, we have talked about the retries. What else? Okay. Okay, let's say that during this whole process, uh, your data is the problem. Let's say PSP is not the problem. So what happens when your data itself is a problem? So we need some mechanism to sort of handle corrupted data as well. So normally what happens is that if we have two components such as a payment service and here's your PSP again, and if your data has some bits of problems and for some reason it's not making through, then the best way is to sort of add it in a queue and let it wait. Not let it rot, but let it wait till somebody attends this queue. Normally, you can call this as a dead letter queue. Oh. Dead letter queue. So normally, if something's wrong with your data, eventually this queue will be processed or checked. If your data is corrupted, if some bits of it has been lost, then it's always better to sort of drop it. But if there has been some discrepancy from the side of the payment service, then it's always better that somebody looks at it, sort of makes sure that the problem is resolved, and then you can take the flow from here. So this sort of helps. Also, this sort of reminded me that we can also use a queue when we're talking about scalability as well. So whenever we're dealing with two components and we want to make sure that we don't lose our data, this also sort of comes into the reliability factor as well, is that we make sure that we can be a reliable service for our customers, which just means that, we won't lose your data, or at least we'll try to. So whenever we're in the payment service, I'll be drawing this diagram for the 100 time again. So this is your PSP, and let's say you have loads of data coming in and something over here at the PSP side fails again, some component fails. So how do we prepare ourselves to make sure that the data that we are collecting from the users, which is of course their money and the data around their money, then how do we make sure that we reliably transfer it to the PSP? Again, we will be using a queue over here, and we'll sort of get rid of this particular motion, and we are gonna make sure that all of our data lands into our queue first, and then it's consumed by the PSP. So you can use, let's talk about the tool later. So this particular architecture can be termed as, the classic pub sub, where your PSP or some component of your PSP acts as a consumer, and the payment service acts as a publisher. So yeah, so this would sort of, enhance the reliability factor as well. As for the tools are concerned, the most popular ones used within the payment systems is Kafka, but Apache Kafka. But if you have any other preference, you can follow it. Just make sure that you have this in place just to make sure that you enhance your reliability a bit better. Cool. So we've talked about the dead letter queue. We have talked about the pub/sub pattern, which sort of enhances your data reliability factor, and it also serves the scalability. All right, coming to let's scroll up a bit and let's mark it as done. And now we're gonna talk about the fault tolerance part. So this happens to be our fourth point. All right. So you might have this thought that even the reliability factor or the reliability section sort of deals with, the conventional fault tolerance occurrences, such as when we're talking about dead letter queue or when we're talking about the pub/sub pattern. So it also deals with certain scenarios which can occur within the fault tolerance section. So yeah, that's true. But the major problem which can occur, which is like the primary fault tolerance problem, is when your payment system and your PSP, oh God, I should have just copy and pasted this diagram. Okay, so the main problem is when your PSP is sort of your payment system is communicating with your PSP and something goes wrong in between, and someone, either part of the component, sort of loses track of your payment, which ends up with the customer paying twice. So how do we make sure that this particular problem does not occur? So because this is like the primary problem within the fault tolerance section. Like, this is the king of faults that might happen to your system. So how do we go around about it? Okay, so the concept used is to use. So let me sort of clear this out first, and let me draw the diagram in more detail, which will sort of eventually help you understand it a bit better. So this is the user. It's communicating with the payment system, which furthermore is communicating with the PSP. Okay, so what do we do when something like that happens? How do we make sure that our user is not paying 2x, as mentioned before? So the idea being used over here is to use idempotent keys, which is just that the user can generate a UUID. Make sure you use the UUID 7 over here, and you generate it along with your payment, and you send it with your data over here. As this is transferred over here, the PSP, so you can save this UUID key within your database as well. So before sending it out, obviously you'll be storing it within your database. So this can sort of serve as like one unique identifier, which can be checked if the payment is made again, or if due to some fault it has been transferred to the payment system again in the same format, or to the PSP. So if you're using these keys at your payment service or the PSP itself, and when they're saved, then obviously since UUIDs are unique, they won't serve the duplication case. So this is like one escape from having such a scenario. where you can sort of make sure that your customers don't leave your platform in a very, very unhappy state. Okay, so yeah, that's about it. And the last point, so we've talked about fault tolerance, and now we are left with encryption and data integrity. All right. So how do we make sure that, you know, the data that we are saving sort of complies with, you know, certain global compliances, and you know, it just doesn't, you know, is vulnerable for the hackers. So obviously the very first thing that comes off the bat is that, hey, is your platform using the, oh, I forgot to write the heading, so let me just add it in real quick. So we're talking about data encryption over here. So obviously the very first thought that would sort of strike you is that, hey, is your platform using HTTPS? So if it's not, then make sure it is. Okay, that sort of serves half of the purpose, because it would sort of help your data in transit. When I say transit, it means that whenever your data is going from one source to another source. So this sort of helps. Okay, but this is half of the solution. Since if we sort of talk about the OSI model, we have to make sure that our data is protected within 2 layers, 3 layers if we sort of expand it. The very first one is application. So HTTPS sort of helps here. Next, we want to make sure that we should get some protection at the session level as well, at the transport level, and at the network level. So when we're talking about network level, obviously, if we're using a particular cloud solution, we can make sure that we're using some sort of a VPC, which is like a subcomponent of any cloud, virtual private cloud. If you don't want to use it, if you want to go about your own solution, then you can consider having some sort of a VPN over here. At session layer, or somewhere in between session and transport layer, we can make sure that we are using TLS, which is like a improved version of SSL, but it's, since SSL sort of deprecated in 2011, TLS is something that we are talking about. So this over here, from HTTPS to TLS, this goes hand in hand, and it serves a purpose of security for you know, for these 3 pointers within application, session, presentation, and transport layer. Specifically session and transport layer. But since we have started from HTTPS, so that's how I've connected it. Cool. When we're talking about, so this sort of addresses the data transit, but we also want to make sure that data at rest is also at rest. So this would obviously be some sort of configuration that we can do within our databases. And also they're also default provided, and you can also choose to select if your data would be encrypted, and you can also choose encryptions. Normally it's AES 256. It's like the advanced level of encryption. Alongside with that, just to make sure that you're escaping any sort of vulnerabilities, make sure that you're thinking about backups as well. The frequency depends on you and your infrastructure, obviously. So yes, this looks good. I think we have covered, yeah, we've covered quite a lot of ground here. So yeah, this is how you will paint out your basic payment system. Cool. I hope you liked the video. So yeah, if you have any comments, please drop in the comment section, and I'll see you in the next video.